Thin film interference. We've talked about two-slit interference, which was solely due to the phase between two waves being produced by the path difference. That is, our phase was 2 pi divided by lambda, where delta r was our path difference. This is exactly what we did in two-slit interference. Now we look at thin film interference, where the phase between two waves is produced by two effects, path difference and reflection. That means then that the total phase between the two waves has a piece that's path difference and the other one that's due to reflection. Because there are now two pieces to the phase, you'll find that thin film interference is more involved. In other words, it's trickier simply because no one can no longer write that delta r equals to m lambda, integral numbers of wavelengths, gives you constructive interference, or that delta r gives you odd half multiples of lambda, gives you destructive. That's not possible anymore, because the phase difference is only half of the phase. So you must be careful with thin film interference. An example of a thin film is gasoline on top of water. Over here on the right you see an image where you get these colors or rainbow colors coming off of this thin film of gasoline. So picture-wise, I imagine that I have light coming from air, I have gasoline, and underneath it I have water. So what you're seeing here is that I have incident light. The incident light is going to reflect off the surface. As it reflects off the surface, I'm going to call that ray number 1, but the important point is, depending how the index of refraction between the incident light and where it's being refracted into, there's now going to be a phase due to reflection. Part of the incident light now refracts and then reflects off the back surface and now is coming back up. Even though there's light being reflected off the boundary between air and gasoline, I'm not showing it, but what you're seeing here is that I have two rays, ray number 1, ray number 2, that are now going to interfere with each other. The important piece is that the green wave travels farther than the blue wave, and therefore develops a phase difference between ray number 1 and ray number 2. How waves number 1 and number 2 interfere, that is either constructively or destructively, will depend on the total phase between the two waves, where the phase total is that due to the path difference plus the reflection. Let's summarize the situation. The top surface has both reflection and refraction. So I see the incident light, the blue here is the reflected, the refracted wave is this green wave going into the surface. Now that wave 2 is refracted, it reflects from the bottom surface down here and it passes back up through the film, eventually re-entering the air. This implies that wave number 2 traversed the thin film twice and traveled farther than wave number 1. So when I look at the path of the refracted wave, wave 2, the path difference is in twice the thickness of the film. So if I write out the phase due to path difference, it's going to be 2 pi divided by lambda delta r. So therefore, delta r being 2t then gives us 2 pi divided by lambda times twice the thickness. There's one piece missing. The refracted wave is in index n here. In other words, this wavelength is in the refraction medium, not in air. Since we're typically talking about the incident light in air, we have to compare the wavelength in the refracted medium to that of air using the relationship that lambda of n is equal to lambda naught divided by n, the index of the refraction medium. We said here that when wave number 1 is reflected, that there's a phase upon this reflection. This is what I will now go on to explain. Phase due to reflection. Whenever waves reflect at a boundary, it is possible for waves to change phase. The way I'll do this is a demo with the wave machine. Here is a wave machine, and what you're going to see here is that at this end, these rods are free to move. Here comes the wave. Let me translate what just happened. So what you're seeing here is that you have the incident wave, and you could see that this is the wave velocity right here, and that the wave is a vertical wave pulse. So it comes and it hits the end, and this is the wave now being reflected, and you could see that by the direction of the velocity. So the reflected wave, when you see this, if it hits a soft end, does not change phase. When a wave interacts with the soft boundary, it does not change phase, so therefore the phase of reflection is 0 when you interact with the soft boundary. Now I'm going to do the same thing where I'm going to send a wave pulse along the wave medium, but this time the end is fixed. So you can see I got the clamp boundary, and it's shown right here where the last rod is clamped fixed so that it can't move. Here comes the video. So let me translate the video. Again, I start off with the vertical wave pulse. It's moving to the left. That's my incident wave. Upon reflection from this hard end, you see that the wave gets inverted. But if the wave is inverted, that means that the phase change is 180 degrees or pi. So the reflected wave has a phase change of pi upon reflection of a hard end. When a wave interacts with the hard boundary, it changes phase by pi. Therefore, the phase of reflection is pi for a hard boundary. Two cases. When light travels from a lower to a higher refractive index, the lower index is soft, the higher index is hard. The reflection at the boundary causes a phase change of pi. Picture-wise, I imagine two boundaries, N1 and N2. And in this case, N2 is greater than N1. So if I look at the wave, it's got to be doing this. That when it reflects here, there's a phase change of this wave, and it now has a phase of pi. On the other hand, when light travels from a higher to a lower refractive index, remember higher is the hard, lower is the soft, the reflection at the boundary causes no phase change. So when the wave comes in, there's no phase change at all. All thin film interference, there are 3 layers and 2 boundaries. 2 boundaries means the waves cross the boundaries 3 times, and therefore we must account for 3 phase changes due to reflection. There are 4 possible cases. The incident wave reflects off boundaries 1 and 2. That's the first reflection. The refracted wave is going to reflect off of boundary 2 and 3. The second phase. But there's a third phase because now the refracted ray is going to cross between boundary 2 and 1. There's a phase change as it, even though we don't look at this reflected wave, there's a change phase in this phase. So the refracted ray, we have to account for 2 phases, Phi2 and Phi3. There are 4 possible cases where I assume N3 is greater than N2 greater than N1, and you could see that I've labeled N1 in light blue. I've labeled N2 in this lime green, and I've labeled N3 in this pinkish fuchsia color. All of these 4 cases I have an incident ray in black. The reflected ray I'm going to draw in green. So what is the phase? When I look at wave number 1, I'm going from N1 to N2, but N1 is smaller than N2, so I'm going from a softer to a harder boundary, so I'm going to get a phase change of pi. So in this case here, this first phase is pi. Wave 2 has 2 phases, so as it goes from 1 to 2, and it reflects off the back end here, note that I'm going from a lower to a higher, so I get a phase of pi. But now, as it crosses from 2 to 1, I'm going to get a phase of 0 here, since I'm going from a higher to a lower. So when I'm looking at this here, I'm going to get N2 less than N3 gives me a phase of pi. And as I go from n2, which is greater than n1, I'm going to get a phase of 0. So summing these two here, I get 0 plus pi. That tells me that the wave that is refracted will then have a phase of pi overall. Since wave 1 and wave 2 have a phase of pi each, there's no phase difference between wave number 1 and wave number 2. So after doing this first case, you could see that wave 2 is more involved. So let's do all of wave number 1's to just get that out of the way. So looking at wave 1 in the second case here, I'm going from a softer to a harder. So therefore, I get a phase of pi. And this other one, I'm going from a harder to a softer. So then I'm going to get a phase of 0. And here I'm going from a harder to a softer, so I'm going to get a phase of 0. So in waves number 1 in each of these cases, since I'm going from n1 to n3, that gives me a phase of pi. In this case here, I'm going from n3, which is greater than n1, I'm going to get a phase of 0. And then finally, I'm going from n3 to n1, which then tells me I get a phase of 0. Now let's focus on wave 2. Here I'm going from n3 to n2. So if I go from n3 to n2, I'm going from a harder to a softer, so therefore I'm going to get 0 phase. But then, so that means from here to here, I'm going to get 0. And then if I go from 3 to 1, that means here I'm going from a harder to a softer. I get a phase of 0, so therefore 0 plus 0 gives me a 0 phase, so therefore wave number 2 has a phase of 0. If I look at the third case here, I'm going from 2 to 1. That's going from a harder to a softer, so I get a phase of 0. But then I'm going from 2 to 3. As I go from 2 to 3, we see that 3 is bigger than 2, so therefore I get a phase of pi. So the overall phase is then going to be 0 plus pi, which will be pi, so I get a phase of 0 in that case. Now let's go to this last case here. So now I'm going from 1 to 2 here. So 1 is smaller than 2, so I get a phase of pi here. Then I'm going to go from 1 to 3, but 1 is less than 3, so I'm going to get a phase of pi. So this gives me pi plus pi, which is 2 pi, which is the same as 0. So the phase of this wave is 0 here. In the first case, if I look at phase of 1 and phase of 2, they both have the same phase, so there's no phase difference upon reflection. Case number 2, the phase of reflection is pi and 0, so therefore that phase is pi. Looking at the third case here, you could see that it's similar to 2, so the phase is pi. But in the fourth case, you could see that these two waves have the exact same phase, so their phase due to reflection is 0. We've now completed how you get a phase upon reflection. Now let's go to path difference, the total phase and interference. Now I want to incorporate both phases. The total phase is due to the reflection plus the path difference for each of the 4 cases that we just looked at. In the 4 cases that we just went over, we saw that in case 1 here, the reflection was 0, this guy was pi, this guy was pi, this guy was 0. Now I want to incorporate the phase due to path difference and then calculate the total phase to look at situations when I have constructive and destructive interference. Case 1, we had a reflection phase of 0. Now for the path difference, note that the wave in medium 2 travels twice the distance. The path difference, which is equal to delta R, is then equal to 2t here. For constructive interference to occur, the phase phi of path difference must be a phase of whole wavelengths. The phase difference must be multiples of 2 pi, 2 pi, 4 pi, 6 pi, or the wavelengths, or the path difference must be in whole wavelengths in the index of n2 of lambda, 2 lambda, 3 lambda, etc. So the condition for constructive interference is that delta R is equal to 2t has to be multiples of whole wavelengths, where m in this case can never have zero value, because that means that the thickness of the film is zero. It's not possible. So it starts at 1, 2, 3, 4 on, etc. here. Therefore, the phase due to the path difference will then be 2 pi, 4 pi, etc., or 2 pi times m. That's what guarantees constructive interference. So, putting it all together, the total phase is the combination of reflection plus path difference. We already saw that the reflection was 0, and the thickness of the film, which is related to this phase, must be then 2 pi times m. So therefore, the total phase is 2 pi m. If I always have a phase of 2 pi or multiples of 2 pi, I will always have constructive interference. Or stated differently, the thickness of the film must be whole wavelengths. On the other hand, for destructive interference to occur, the phase must be a phase of odd multiples of half wavelengths. For destructive interference to occur, the phase must be a phase of odd pi's or odd multiples of half wavelengths. In other words, the phase due to path difference should be pi, 3 pi, 5 pi, etc. Or the path difference has to be half of wavelength multiples, or 3 halves or 5 halves. That is, the condition for destructive interference then is that the path difference 2t must be odd 1/2 multiples of the wavelength, where now we include 0. And the path difference must be these odd pi's. Sum up the whole thing here, the total phase, due to reflection and path difference, the reflection is 0, but now I need the path to be odd multiples of pi, which gives me that the total phase is odd multiples of pi, and this is always destructive. The thickness of the film then must be, in order to be destructive, this multiples of odd 1/2 wavelengths. Now there are only 2 possible cases. Case 1 that we just looked at, we had a phase of reflection of 0, and you could see that the first and the fourth case have a phase of 0. But if you look at the second and the third case, they have a reflection phase of pi. So now this is the second case that I want to look at. When we look at a reflection phase of pi, what that means here is that waves 1 and 2 start out of phase immediately. So if I want constructive interference, I have to have a phase shift of pi or multiples of odd pi in order to get constructive interference. For constructive interference to occur, the phase phi path difference must have a phase of odd multiples of pi. If this is the case, then when I look at the total phase, the reflection plus the path difference, I start off with pi, but if I have odd multiples of pi, 3 pi, 6 pi, etc., then the total phase becomes 2 pi, 4 pi, 6 pi. But then this sets the condition for constructive interference. So the path difference 2t must be odd 1/2 multiples of the wavelength in the index of refraction. In that case here, you could summarize this by m plus 1/2 times the quantity lambda sub n, where m now does include 0, 1, 2, 3, or the phase has to be odd multiples of pi, which would be m plus 1 times pi. So this is just the opposite of what we saw in two-slit interference. So you gotta be careful. when you have this phase difference of pi, destructive and constructive equations appear to switch. For destructive interference, we want to keep the total phase as odd multiples of pi, because we want to keep it with the phase of pi. For destructive interference to occur, the phase of the path difference must be a phase of even multiples of pi. So when I sum up the total phase, reflection plus path difference, I start off with this original phase of pi, and then my path difference can't be 0, so it has to start off at 2 pi, 4 pi, 6 pi, etc. So therefore the phase is in 3 pi, 5 pi, etc. But then this sets the condition for destructive interference. So if the path difference is 2t, it has to be multiples of whole wavelengths, which means that m times the wavelength of the index of refraction has no m value of 0, but starts at 1, 2, 3, and then the phases are factors of 2 pi, so I get 2 pi m. And now I want to apply all this thinking to example 33A.4. A disabled tanker leaks kerosene into the Persian Gulf, creating a large slick on top of the water. If you're looking straight down from an airplane while the sun is overhead at a region of the slick where its thickest at 460 nanometers, for which wavelengths of visible light is the reflection brightest because of constructive interference? Draw a picture of the situation. B. If you're a scuba diver diving directly underneath the same region of the slick, for which wavelengths of visible light is the transmitted intensity strongest? Draw a picture of the situation. So the thin film has air, kerosene, and water, where the thin film is set up by the kerosene right here. They tell us that the thickness of the kerosene is 460 nanometers. The index of water being the highest, followed by kerosene and air, we then know what the reflection phase is. Incident light going from a lower to a higher index of refraction, I get a reflection phase of pi. For the phase 2 here, note that I'm going from kerosene to water, so I'm going from a lower to a higher. That automatically gives me a phase of pi. And then I have the second boundary. I'm going from a higher to a lower. That gives me a phase of 0. So therefore the total phase of the second wave is then pi. In other words, the phase difference between these two waves is 0. So now that I got my phase of the reflection, I now got to go look for the path difference. So the phase difference due to path difference is then going to be 2 pi divided by lambda sub n times 2t. Since the reflection part of the phase is 0, if I want constructive interference, then this path difference phase must be for constructive interference too. It means that the phase has to be 2 pi times m, where m then becomes 1, 2, 3. We cannot have 0 because that would mean that the path difference is 0. In other words, no thin film. To determine when we see a constructive interference region, this will depend on the wavelength of light, lambda naught, that is, the wavelength of the incident light. But the wavelength in kerosene is equal to the wavelength of light in air divided by the index of refraction of the kerosene. Taking this phase relationship that we have up here, I now solve for lambda n. So going through the algebra, we get that the wavelength of light that is incident on the kerosene is then going to be equal to 4 pi n of kerosene times the thickness divided by 2 pi m. Let's calculate the possible visible light wavelengths that cause constructive interference. The range of visible light is 400 to 700 nanometers roughly. Cleaning up this algebra over here, I get that lambda naught is 2 times the index of refraction, thickness divided by m, If I put in these values and multiplying it, I get 1104 nanometers, where this is the M value. So for M equal to 1, I get 1104 nanometers. For M equals to 2, I get 552 nanometers. For M equals to 3, I get 368 nanometers. So this guy here is outside the visible region. If you look at 552 nanometers, it falls within the region. If you look at 368, it falls outside of the region. So the only possible wavelength is 552 nanometer light. You can see that 552 nanometer light is this greenish color. B. Maximum transmission of light into the water occurs for waves where reflection is 0, or destructive interference occurs at the surface. So the light that is destructively interfered at the surface to conserve energy must be transferred into the ocean. Therefore, the path difference has to be such that 2t is equal to m plus 1/2 times the wavelength in the kerosene. Solving for the wavelength that then gets transmitted here, I'm going to then have 4 the index of refraction of the kerosene times the thickness divided by 2m plus 1, which then gives me 2208 nanometers divided by 2m plus 1. What's tricky here is that for constructive interference, m starts at 1, 2, 3, etc. But for destructive interference, it includes the 0. And that's because for constructive, you need a path difference that's not 0. Here, you don't start off at 0. You do start off at 0 because of this m plus 1/2. The sequence of m values are, for m equals to 0, I get 2208. For m equal to 1, I get 736. For m equal to 2, I get 442. And what you're seeing here is that this is outside the visible region, this is outside the visible region, and anything above that is outside the visible region. This is the only one that falls within the visible region. You can see that this color is in the violet region.